Assalamu alaikum. We are at the 13th lecture of Software Quality Assurance. In the last 3 lectures, we developed a strong link between software design and software quality. In order for us to have high quality software, we must have high quality software design. Today, we are going to talk about programming. Programming is probably the most enjoyable and fun part of all the software engineering activities for most of the people. Most of the professionals in the software engineering community enjoy programming more than any other activity. Today we will look at the link that exists between programming, or coding some people like to call, and quality assurance. The act of programming produces the primary products that are the executables of a software development effort. We know that we have to have high quality requirements, we know that we must have good quality design, but we cannot execute requirement set, we cannot run the design products. We can only execute code or programs. And so we must have high quality code or high quality computer programs. All prior activities culminate in the development of software, in the development of these programs. And programming is done in a programming language. We have to leave behind the design languages, the design methods. We have to leave behind natural languages. We have to deal with computer languages. There are a number of them, as we will see. Look at the characteristics of some of them. Some of them are high-level languages, some of them are low-level languages. So all of us, whether we are in the designing activity or we are requirements engineers, we are testers, we are maintenance specialists, we must know programming languages. Because all the executable code, all that runs on the computer is written in the computer programming languages. When we examine the code, the source code, we find that all 4 categories of software defects are found in source code. We have errors of commission, we have errors of omission, we have errors of clarity and ambiguity, and we also have errors of speed and capacity that originate in the source code. However, errors of commission, that are mistakes, are the most common problem in the code which is under development. So whenever the programmer still has the control of the program, the most prevalent errors are errors of commission. The most surprising aspect of coding defects is that more than 50% of the serious bugs or errors found in source code do not originate in source code. And so this is interesting that source code which is ultimately going to be executed on the computers is not responsible for more than 50% of the errors. These 50% or more errors are coming from the design activity or even prior from the requirements activity. So this is because the design was misunderstood or the designers misunderstood the requirements. So the origin of these defects is not source code. The origin is either the design activity or the requirements process. You also have to recognize that because of the nature of the software, it is one of the most difficult products in human history to visualize prior to building it. That is, I cannot visualize how a software product would look like unless I build it. Although the same can be said about complex electronic circuits, which also has the same characteristics. But because of the advances in electronics, that is still easier compared to visualizing software products. So visualization is a problem when we compare with other engineering disciplines. In the recent developments, there's a lot of emphasis has been paid to research in building syntax checkers and editors which are contained in integrated development environments for modern computer programming languages. These environments have the capacity to detect many of the simple defects that actually originate in the source code or when originate while doing programming or coding. These errors are like missing a parenthesis or errors in looping, but they also have the capacity to measure and correct structure and excessive branching, these integrated development environments I'm talking about. But this facility has only limited capacity and can only capture simple errors. The kinds of errors that are not captured or detected easily indicate deeper problems of misunderstood designs, problems in algorithms or those associated with documentation of wrong requirements. And these are the real problems that programmers have to deal with, have to try to clean their code from, so to speak. There is an added problem, and that is that at least 500 programming languages exist, and they have been used in the last 50 years or so. And characteristics of each language are different from characteristics of other languages. Coupled with the factors such as human attention spans and capacities of temporary memory, the use of programming languages can induce or inject certain types of defects in the programs. And so this means that each language or groups of languages tends to have patterns of defects. However, within a group, these patterns change from language to language. And there is no empirical data that strongly typed languages have lower defect rates than weakly typed languages, although there is no counter evidence either. But in most of the computing environments, strongly typed languages are preferred over weakly typed languages. But one thing is sure, and that is in all programming languages, branching errors are endemic. That is, branching to a wrong location for execution of a segment of code. And so as a mechanism to improve quality of software, quality of source code, the programmers and the management needs to learn this, that the branching errors have to be eliminated, preferably by prevention, but can also be done through removal. Now let's talk a little bit about defects in higher level languages. There were certain languages, for example Ada or Modular 2, which were designed to minimize common kinds of errors, such as mixing data types or looping incorrect number of times. These languages force us to structure our programs in such a way that we try to that structure minimizes these kinds of errors. Of course, your typographical or syntactical errors still occur, and they occur even with best of the programmers. But more troublesome errors have to do with logic problems or incorrect algorithms. And that's an area where programmers need to improve if they want to produce high quality software. Now this also goes back or links back to the design of the component, also known as detailed design. If designers are well aware of the application domain, and of course they must be aware of computer science data structures and algorithms, they should be able to develop an algorithm or suggest an algorithm which is going to minimize these errors. So you can see the link that exists, that starts with the requirements, goes into the design, and then into the programming. All of them are linked with the concept of, or the goal of, developing a high quality software product. A common form of error for both procedural and non-procedural programming languages has to do with retrieving, storing, and validating data. That is an essential part of any computing system. Languages are used to access data from databases or from the user, to store it, to validate it. This is a very common practice. All languages must support these functions. Sometimes it happens that wrong data is requested. So language designers as well as language users have to be sure as to what kind of data is being requested or being passed. Data mismatches are a common problem in source code. Programming, whether it's done in assembly language, which is a lower language, one of the lowest possible languages, or higher level languages, is a complex intellectual challenge with a high probability of making mistakes from time to time. As I said, good programmers make mistakes. You can compare this with a newspaper. Every good newspaper has typographical mistakes in it. Many good books, even with lots of reviews, many people looking at them, and the publishing houses looking at them, still have typographical errors. And so these are minor issues which are usually even caught by the integrated development environments. So the focus should not be on these. The focus of programmers should be on trying to eliminate the more complex algorithmic and branching kinds of errors. Low-level languages also have their own sets of problems. Since low-level languages are used to manipulate registers and processes directly, and they requires that programmers, that is the coders set up their own control loops. Common errors involve failure to initialize registers. As a result, previous register values may be used, going through the loops accurately, the correct number of times, and not allocating space for data and subroutine. And so, as a result, lower level languages are a difficult thing to program in. Programming in higher level languages is far more easier. And for weakly typed languages, mismatched data types are the most common types of errors. As I had said before, that usually programmers prefer to use strongly typed computer languages because it allows them to have another safety net, that whenever they will make a mistake, it will be caught. Whenever they'll have a data type mismatch, that will be caught by the compiler. Let's now discuss some quality practices for general purpose programming. This discussion is split into two parts. In the first part, I will list 5 quality practices, which you will see on the screen. And then we will take each one of those 5 and discuss them in much more detail. So let's begin. Here on the screen you are seeing quality practices for general purpose programming. It lists 3 practices. Number 1, use the highest level programming language possible. Number 2 says use integrated development environment or environments. And number 3 says adopt a coding standard that prevents common types of defects. All of them are related to quality, of improving the quality of the software code. We have just seen first three quality practices for general purpose programming. We'll discuss them in a little while. But before we do that, let's see 2 more quality practices for general purpose programming. Here you can see that 2 practices are listed: prototype user interfaces and high-risk components. And second is define critical regions. Now we have in total 5 quality practices for general purpose programming. What we will do now is that we will take each one of them and see what they mean, and we may find that each one of these practices has 1 or more sub-practices. So the first one is use the highest level programming language possible. You have to realize that code written in higher level programming languages is easier to read and maintain. I think there is no disagreement on this. A piece of code, a program which is easy to read is easy to maintain. A program which is difficult to read is difficult to maintain. So they say that any fool can write a program that a computer can understand. Good programmers write code that humans can understand. That's a very strong message. There are several practical factors which influence the selection of a programming language, because languages are going to communicate with the computer as well as the humans. So it's not just purely a technical decision. One of the factors is technology trends. Are we following the latest technology trend? Are we doing web programming, for example? Or are we buying into a certain development philosophy. That is a factor which is going to influence the selection of a computer language. Second is the organizational informational technology strategies. This means that what is the policy, what is the strategy of a company vis-a-vis information technology? Is it going to do development in open source paradigm, or it is going to buy into a proprietary technology? That is going to have a major impact on the selection of the programming language. Remember, we talked about design and implementation constraints when we were discussing requirements? Here they come again. Customer restrictions on programming language selection, because that's the language the customer wants software developed in, because that's the language that they have been using, or they have other products which were developed in that language. And they want to sort of keep that homogeneity within their computing environments. So that is a factor that can seriously affect or influence the selection of a programming language. Then we have the experience of the development team. Yes, we can select a great language, but what if we don't have any experience with that? The project is due in short intervals, and delivery has to be done as soon as possible. No doubt that professionals should be able to learn new language fairly quickly, but fairly quickly does not mean with zero time. If they want to learn a language, they have to spend time learning on it, and many languages have a steep learning curve, and so that is a factor. And finally, features of the programming language that are necessary for the environment as a whole. For example, one important feature that comes to mind is the ability to interoperate with external systems. Does this language that you are choosing has that facility? Can it communicate with other languages? Does you provide that capacity, facility? So these are the factors that also play a deciding role in the selection of a programming language. There's another interesting thing, that the complexity of software systems is growing quicker than our ability to develop software solutions. For example, the productivity of computer personnel increased about 6% per year during the 1990s, whereas the growth in NASA mission software is about 25% per year. Our productivity is growing by 6%. The growth of software in one organization is growing by 25% per year. So that is something that has to be kept in mind while selecting a language. On the other hand, productivity is constant in terms of program statement size. Here is an example. Writing 10 lines of code in assembly language takes as much the same time as writing 10 lines of C++ code. But the functionality developed in those 10 lines of C++ code surely would be much more than the 10 lines of assembly code. So what we are doing, we are actually shrinking the size of the programs by using higher level computer languages. So not only that, but there are some interesting facts that the productivity of programmers is improving by using high-level languages. Fred Brooks, who is a famous author and teacher and researcher in software engineering, has said that the advent of high-level programming languages had the greatest impact on software productivity, because there was at least a factor of 5 improvement in productivity. That is a major success. Another factor is that the use of high-level languages results in high reliability software. That is, software whose reliability is more independent. Now, we have high reliability, we have higher productivity, we have higher quality, program size is shrinking by using higher level programming languages. So that's the suggestion. The next quality practice that we talked about was use integrated development environments. These are commonly known as IDEs. I'm sure you have heard the term and you might have used any one of them. Typically, these software suites include an editor for writing programs, a compiler for compiling the code, a make utility which puts together the project, a profiler which gives a profile of the program. It can also have other quality assurance mechanism included in them, like memory leaks, like monitoring memory leaks and measuring different kinds of cyclomatic or essential complexities. Typically, a debugger would also be included. And similarly, other tools can be made part of these IDEs. Recent IDEs, or integrated development environments, include tools to model software design and implement graphical user interfaces. So all your design and development work can be integrated, and as a result, whenever there is need to make changes in software design, those then will be reflected in the code also. And so this is a very good thing. The productivity will improve, and these tools, if used properly, can improve your productivity 100 times. That is double your current productivity. So integrated development environments also help us in identifying true coding defects. We had discussed this concept a little earlier in the lecture. So up to now we have discussed two practices. Now we are going to take the third practice and discuss different sub-practices that can fall under this. The third practice is that adopt a coding standard to prevent common types of defects. Now, coding standards are controversial because the choice among many candidate standards is subjective and somewhat arbitrary. People like certain coding standards, other people like some other coding standards, and there is no scientific evidence that which coding standard is better. So one thing is sure, that some sort of agreement has to be reached so that our code looks like an integrated and uniform effort, just like the design. But standards are most useful when they support fundamental programming principles. And I know that people get used to of writing code in using one standard, and when they are asked to change that, it becomes difficult for them to do so. So it is easier to adopt a standard for handling exceptions, for example, than to identify the amount of white spaces used for indentation. Variable naming is also another issue that can cause a little bit of rift within the development team. So this is a problem. So in order for a company to choose a coding standard, a company or an organization should always ask itself whether a coding standard improves program comprehension characteristics or not. If a coding standard improves the program comprehension characteristics, then yes, that coding standard can be used. But if a coding standard is not improving the program comprehension, that is program understandability or your ability to read programs clearly, then that coding standard should be discarded. Let's now look at different quality practices related to programming and coding standards, because coding is a very vast activity. Programming consists of many facets. There is internal documentation, how you would like to name variables, how would you like to write functions, what are the operational issues, and so forth. So for each of these sub areas in programming, under the same heading of coding standards, we'll now discuss practices which can improve the quality of code or quality of programs. We are discussing now the practices for internal documentation, that is documentation that programmers do within the programs. The first thing that you have to decide is to specify the amount of white space that would be used and where it should appear, before and after loop statements and function definitions. At each indentation level, what is the amount of white space that you want? Studies have shown that if you use 2 or 4 spaces, they improve program comprehension. And that is the ultimate goal of using these sorts of standards. The ultimate goal is for a maintainer to read the code and understand it. And if we can develop a standard which helps us in doing that, then we are going a long way in that direction of improving the quality of the software product. We also have to decide and make a decision, deciding on physically offsetting the code comments from code, that is program structures, when they are contained on the same line. Would we do it in the beginning of the line? Would we do it at the end of the line? How would we do that? And with the new commenting style that the rest of the line, there are certain comments in which you can comment the entire line. You have to take care of things. Where would you put the comments in relation to the actual source code? Then you also have to decide on the use of comments to explain a class, to explain a function, sometimes to explain a variable contained in the source code. Comments can be up from 10% of the total code. When we were discussing different quality aspects in the first phase of the course, we had mentioned an IBM study where the comment density was about 18%, and that helped in finding defects. And so again, this is a decision that an organization has to make depending on the factors that we are discussing. Now, what areas would you like to comment? The suggestions are the key interactions that a function has with other functions and global variables, because these are the things which are not contained in this, in that logical and physical source file that we are talking about, or component. Complex algorithms used by every function. So whenever there is complexity involved, to explain a little bit or to mention that this algorithm is of that type whenever there is exception handling, and behavior and effect of iterative control flow statements and interior block statements. So whenever you have iterative control flow and blocks, where you use blocks in interior blocks in different languages. So you can define a block which does or which captures some set of statements. So these are the areas where you can use comments. You should also note that working examples in the user manuals and tutorials will definitely help the user of the software system. Let's now talk about variable definitions. Variables should be declared as specifically as possible. Initialize them also, and you should preferably have only one declaration per line, one variable declaration per line. The names of the variables should be such that if a domain concept is captured in that variable, that should also reflect in the name of the variable. Secondly, do not use similarly named variables within the same lexical scope. For example, amount is a variable. Don't use amount 1, amount 2, amount 3, unless amount 1, amount 2, amount 3 are entities from the real application, from the real world, because these are going to cause confusions. Consistently use clear and easily remembered names for variables, classes, and functions. This is very important. We talked about having a class aircraft in one of the design lectures. So if you're designing a class aircraft, that should be named aircraft, not a flying machine. You need to follow a uniform scheme when abbreviating names. I understand that in many cases, the complete name of the real-world entity cannot be used. There can be restrictions on the length of the variable name in certain languages. In fact, all languages have certain restrictions. And so it is not always possible to use complete names. We have to use abbreviations sometimes. Be consistent with abbreviations. If you're using underbar or underscore, use that consistently. If you're using dashes and the languages allow that, use that. Don't mix them. That's the point. Don't use local variables to hide declarations at greater scope. Many languages allow you to have variable names repeated in inner blocks, and new programmers think that this is a nifty idea and they use it. What they don't know is that this is going to cause a lot of confusion. Let's say I've declared a variable by name of alpha, and it is capturing some concept, and in the inner block I say alpha. The computer knows it, yes, which alpha is being referred to in which scope, but a casual reader may not know. This is where the confusion starts to get into the maintainer's mind. And never use a variable for more than one purpose. That is, if you're changing scope, if you've declared alpha as an integer, don't redeclare alpha down as a character or as a string or something like that, because it is certainly going to cause confusion. Remember, you have to write the code for the maintenance people. They are the ones who are going to read it. Let's now talk about practices for control flow. Do not assume a default behavior for multi-way branches. That is, whenever you have a situation where you have a complex expression, and that expression can result into multi-way branching. To use a language construct, I would say, if you are in a situation like switch case statement, don't assume that there is a default behavior. Check, and if a default behavior exists, then use it. Secondly, do not alter the value of an iteration variable within the loop. I know languages allow it, but it makes the quality of code poor. It creates confusion. So you have to be explicit in doing things. Another advice would be to use recursion wherever and whenever applicable. Recursion is a good thing. It enables the concept to be documented very nicely. So we know when we see recursion that this concept is being applied. Let's talk about practices for functions. Explicitly define input and output formal parameters. Many languages have this facility that you can differentiate the input parameters as well as the output parameters. And it has an added advantage or added safety factor that you cannot change the value of the incoming parameters. This will explicitly tell the program reader that these are the inputs and these are the outputs. And so safety and reliability of the software will go up. Another advice would be for use with functions and procedures is to use assertions. Assertions are pre and post conditions to verify the accuracy and correctness of input and output of formal parameters. This is a direct quality assurance mechanism. The use of pre and post conditions helps programmers to detect defects closer to their origins. If a function is receiving input or a procedure is receiving input which does not meet the precondition, then that function will not execute. And we will have the detection right there. And if the results produced by the function or by the procedure do not fulfill the post condition, then the error was created or was originated in that function or procedure. And that's a great help in quality assurance. That's a great help in error elimination. It does not allow the errors to propagate. It helps us in finding errors from where they originate. Let's talk about practices for operations. There are certain operations that are used in all programming languages. One of them is conversion of data types. You have to make all conversion of data explicitly, especially if you're dealing with numeric data. Do not use exact floating point comparison operations. You know that the floating point numbers have a degree of to which they are accurate. So if you compare two floating point numbers where their accuracies are different, then you will never get an equality operator result as true. And so comparing floating point, or also known as real numbers, is a dangerous thing. Keep your programs safe from these things. Another thing with operators is that you have to avoid operators in potentially ambiguous situations. I know that the operator precedence is defined. I know that operator precedence is equal in certain cases. And so whenever there is a possibility of confusion, use parentheses to clearly state your operator precedence. You can always overwrite the precedences that are available in the language by putting parentheses or using the language structure that is applicable to define the way you as a programmer want the operators to work. Practices for exception handling include that you have to process all exceptions so that personnel, that is the testing people, the maintenance staff, can more easily detect the cause of exception. We know that exceptions indicate failures. And if we handle only few exceptions and not all, then we will not be able to detect what the cause of the failure was. In order for us to remove the defects, we have to go and find the cause of the failure. For some systems, you have to log important events. I'm not saying you start logging for every application, but in many applications, you have to log important system events. Let's now look at a couple of operational practices. The first is that we're using an integrated development environment. So whenever there's a compilation, don't let any warnings go through. These initially may not bother the working of the system, but these warnings indicate certain problems that can be eliminated by using practices we have just discussed. Secondly, first you have to get your software working, and then you should optimize it. And optimization should only be done to meet the performance goals. The fourth main practice, quality practice, that we just mentioned earlier in the lecture was prototype user interfaces and high-risk components. User interface prototyping helps identify necessary features that software engineers might otherwise overlook. It gives you an early feedback, provides you an early feedback from the customer. Prototyping can reduce the development effort significantly. Prototyping reduces development risk because it allows programmers to explore methods for achieving performance and other high-risk requirements. And so prototyping those requirements which have risk associated with them, or prototyping for user interfaces, is a very good practice. Let's look at the last quality practice that we talked about, and that is to define critical regions. A task that interrupts an interdependent operational sequence before it is completed can leave a program in a vulnerable state, resulting in inconsistencies and inaccuracies. The results can be inaccurate or inconsistent. The solution to this sort of problems are defining a critical region. A critical region acts as if only one statement has been executed. So either all of them are executed or none of them are executed. Critical regions help prevent deadlocks. And for real-time systems, deadlocks are a real threat to software applications. Today, we have talked about software quality assurance and how quality assurance mechanisms can improve our programming product, which is the executable software system. The practices that we have discussed today will certainly lead to a higher quality source code and higher quality product. From the next lecture, we'll take up other interesting topics. So see you then. Allah Hafiz.